We're talking about developing rate from accumulation. Rate from accumulation. So the example we were using before was the volume of a sphere, and so this is now something different. This is I don't know what it is. Any suggestions? So what accumulating quantity could this be for? Population what? Population of animals. Just all animals. Population of all animals.
In trillions.
We don't have to have an application, but all right. So you're going to be sketching some graphs here. So we got a new accumulation function f, and what our goal is to what develop the rate. What's that? This actual accumulation, right? Actual accumulation. So the first thing we did was, just a review, first thing we did was hold on a second. I thought this was ready. Hold on. Stay tuned. What the heck? Oh, no wonder. That's the problem. There we go. Now it's better. Okay. First thing we did was we looked at these. Sorry, the numbers are so small. But intervals of, this is what, 0.2. Intervals of 0.2. And then those were fixed intervals, and x increased through those intervals. And the first thing we did was we sketched the approximate accumulation function and the approximate rate function. So that's your first graph. So sketch approximate accumulation. So yeah, every 0.4, sorry. Yeah. So the h value is 0.4. So we're going to set these intervals at 0 to 0.4, 0.4 to 0.8, 0.8 to 1.2, 1.2 to 1.6, etc. And then, so how many you got? Can you fit 4 in there? Okay. And then draw the approximate rate function based on that approximate accumulation function with these set intervals at 0 to 0.4, 0.4 to 0.8, 0.8 to 1.2, 1.2 to 1.6. Yeah, so the first one, you can just estimate the change in, y is about 4 for a change in x of 0.4, so that makes a nice estimate for your rate. And then you can say 0.6. The next change is about a change of 1. Is that about right? From like 4 to 5. Change in y for the second interval. More than 1? Just for, but wait, this is a rough estimate, so don't make it easy on yourself, right? Make it 1. Make it 1. Make it easy. Oh, you want to make it 1.2? It's easier to divide. Okay. Sorry. So I guess 1.2 is easier. Okay. So should have something like. Okay, and we wrote expressions for both those functions, right? We wrote an expression for the rate function. So only approximate right now. Okay. Yeah. So the approximate rate and the approximate accumulation. We did that in 2 different classes. Make sure you could still do that. But then we said we're going to move on to smoothing this out, right? Kind of starting over, but with a smoothed out version. Right? So now what's the difference? The difference is the interval always has the current x value as the left side of the interval, right? Instead of fixing them first and let x vary through the fixed intervals, now the interval is going to slide with the value of x. Okay, so now I want you to sketch on that second graph now. This is for the sliding interval. You're going to sketch what would on both graphs. You're going to sketch what would represent the approximate rate for the current value of x. Sketch what would represent the approximate rate for the current value of x, and then sketch the approximate rate function over on the left. Does it make sense? So what are you? So what you make a sketch on the right side? You're going to sketch what entity will represent the approximate rate of change. How are we going to build the approximate rate of change out of this approach? So what would you sketch on that graph? No, just look. You've got one. It's just for one value of x. Just for one value of x, right? So just an example for the current value of x that is shown. But then on the left graph. So the left graph, let's represent the one that you sketched. Represent the one approximate rate that you sketched. No, represent the one constant rate that you sketched. You just sketched one approximate rate, right? Okay, how would that be represented on the other graph? You got to think about this now. How would that be represented on the other graph? Okay, so on the right graph, this was what we were after. But I paused it, right? We're in the second, right? Okay, so this particular approximate rate that I'm showing right here, how would that be represented on the graph on the left? Everyone, show me what you got. How would that be represented? Okay, so did you actually get an approximation for the rate? What did you come up with? It doesn't matter, just something close. 5? Did you get something like 5? Around. Okay, 5, 6, 4. This is approximate. This is estimating. Okay, so something in the ballpark of 5. Okay, so then starting at this x value, we're gonna have that constant rate for the next point 4. Is that right? Is that right? So that what I saw was lots of you drew. You took that constant rate starting at whatever this is around point 3, and you said we're going to take that constant rate for the next point 4. That's what most of you drew. So look what happens. If I change x a little bit, is it the same rate or different? So if you drew a horizontal line, is that correct? So how this one rate, how would you represent that rate of 5 over on the left then? How would you represent that approximate rate of 5 over on the left graph? How would you change it? Okay, so how is that represented? What kind of thing? Just a point, right? So we take the rate that we get from this whole interval, we assign that rate only to the x value at the beginning of the interval, because as soon as x changes, we get a different rate. See that? Okay. So you've kind of pinpointed that point, and so now pretending that you would do that for all x values, can you now sketch the approximate rate function, pretending that you would do that same thing for all x values? Go. So I'll animate it. I'll animate for you. So then what will it look like if you were to do that for every single x value? What would the approximate, now we're talking about the rate function, right? Approximate rate function. Is the task clear? What's that? No, it's as if you were doing it for all points. So, no, we're still in the third, still in the second. Still in the second graph. As if you were doing it for every x value. Okay, and then can you define that function? Define that function. So that function that you just sketched over there on the left, let's call it, so it's R, right? It's R. So what is R? Where does it come from? What is it? What is left x now? So when you write the function, just think of it for a particular value. We just think of, so here's x. How would you write the rate of change for this x? How would you come up with a formula that would give you the rate of change for that particular value of x? Well, if you keep it as x, then it's true for all x's, right? Okay, how do we do? Did we get it? So where does it come from? Where does that rate come from? Ah, it comes from the fact that this is not on. Where does it come from? If I want to write the rate of change represented by this secant line, change in y over change in x. So that our function is going to be change in y over change in x. Okay? So we need the change. What's the change in y? So we need the y coordinates of those points, right? It's all about the coordinates of these points. So what's the coordinates? No, you're not listening to music, Peter. Right. See, I told you, I knew he wasn't. Right. Camry, what are the coordinates of the first point there, the left point? No, that point right there. We need, so if we're going to get the rate of change, this approximate rate of change, we need those coordinates. Okay, and then Angela, how about the coordinates of the next point? Right. Yes, that's absolutely. I mean, we've stuck to point 4 here, so if you had point 4, that's valid as well. But that's going to change, so we'll keep it as h. All right, and so then the rate of change is change in y over change in x for that secant line. And that's the approximate rate we're going to assign to that x value at the beginning of the interval. That's why you just got a point over here and not a whole line, right? As soon as x changes, we get a new point. Questions on this? All right, so your curve should look something like this. Yeah. Okay, yeah, so is this, good question, is this approximate or actual rate of change? And so, and Morgan, so they're saying it's approximate. Is it more or less than the actual rates? Everyone has to answer that in your tables. Is this approximate? So do you see that it's approximate? Here's how you can see the best. All right, so here's how you can see it. If I pause it here, if we zoom in right here, so the black is our curve, but I've zoomed in far enough so it appears straight. So that local linearity represents the true rate of change. So see the blue one's at a different rate. See that? So this blue curve that we're drawing is still, it's continuous, it's nice and smooth, but it's still approximate. Okay, and then what did you decide? Is these approximating values too much or too little? The rate is too small, so all right, so then this is what we came up with, right, for the rate? For the approximating rate? Rate function? Okay, and so the last one is, what if we did this all again for us? So you can see daylight there, but the idea of the last graph is that it's a really, really small h, okay? It's a really, really small h. So same thing again. I want you to sketch the approximating, what would represent the approximate rate, but now we're saying we're really close, like so close that we can't distinguish between approximate and exact. And then, again, sketch a point for that rate, and then sketch a representation of all the points for all the rates. So, are we going to get the same curve again? How will it be different, Genevieve? How will it be different?
Well, we decided that this was too low of an approximate,
right.
So all the rate values would be
good. Yeah, good. Okay, so what you're working on now is, so I'll make h small, and we'll see what happens here. Ready? I'll make h small. Did you catch it? So I just made h a lot smaller to kind of match up with your third graph there. So I'll go back to point 4, and I'll show the exact also. Okay, so the light blue is everything for point 4, and now the red is that h were really small. So if we're going to write then the exact rate function, how do we write the exact rate function? So this would be like r. So now this is what we call r sub f. How do I write a formula for the exact rate function, which is what you sketched in your third graph? Oh, Jose, go ahead. Okay, so the point is that we're doing the exact same thing. We're still taking a little change, or taking the change in y. But now h is, that's like it's equals with a dot above it. It's like essentially 0. It's essentially 0. Another way to say it is what Jose said. This just means let h get so small that you can't tell the difference, right? It's so small that you can't tell the difference between approximate and exact. So 2 different ways to write it. Yeah. No, you just set h. You just define h to be small enough. Like I have it up to 0.005. But no, GC, because it's not really defined, right? It's not defined what value you're saying h is. It's more an idea that h is super small. Okay, and so this is our exact rate of change function, which you should recognize. Okay, the exact rate of change function is what function? Derivative. So what's the big deal with average rate of change? Right, so we said, why is there so much emphasis on constant rate of change and average rate of change in our program, math ed program here at ASU? So this is answering the question, why is there such a big emphasis on average rate of change? What's that? Yeah, so how is it the basis of derivative? He says the basis of derivative. How is it the basis of the derivative? Yeah, exactly. It's this thing right here. I mean, a derivative is an average rate of change, just for a very small value of h, right? That's what a derivative is. It's the average rate of change. It's the constant rate, right? The constant rate that gives you the same change in y for the same change in x. And if you make h small enough, then that is the exact rate of change. average rate of change is the constant rate that gives the same change in y as the function does. And when you do that for small enough h, you get essentially the exact rate of change. And then you do that for all values of x, you got the function, right? And that's what the derivative is. Okay. Any questions? So I'm thinking that if you want to build this for extra credit, you can build this for extra credit in the course if you want. And it would be if you build it, if you do a good job, it can be significant. So I showed you colors, didn't I? If you just do comma color equals, and you set it from you get all possible colors in the range from 0 to 1. What's that? Do you have a PC too? Sure. Yeah, because I want you to focus on falling marbles. Focus on falling marbles for now. So don't start working on this until you've got falling marbles under your belt. What's that? No. No. So this would be an extra credit. Now, let's see here. And there's a lot to this. There's lots of. So here's view 0. View 0 just has the increasing x and shows the h. Yeah, so I'm just using symbol. Well, no, actually, I dragged an image. You could on a PC you could do this with symbol, absolutely. I dragged an image onto a point, command line of a point. But the point is changing, right? The point is changing. Yeah. Yes. Yeah. So the point of this is not to get this really nice brace, okay? I think it's really nice visually, but that's not the point of this. The point of this is using the stuff we're learning now. All the stuff that we just learned is essential to writing it, right? So that's the point. So yes, if you just want to do a straight line with two little things, great. Okay, so this is view 1. View 2. View 2 then shows the approximate accumulation function emerging, okay? And then it would work for different values of h. So choosing different values of h, it will work. So the way I have it is when h is 0.4, that's when the bracket shows up with the h, but as soon as change h from 0.4, that goes away, and you just see see the graph, okay? And then view 2 shows the transition here both, so it's both the chunky method and transitioning to the sliding interval. And then view 3 shows the sliding interval and the two vertical lines. View 4 adds the secant line. Again, for all these views, if you change h, it should work. If you change h for any of these views, it should show accordingly. And then view 5, I show the approximate rate function for the current value of h. View 6, add the formula. View 7, add the exact rate function. What's that? It wouldn't matter. So you can, it'll be easier, right? It's going to be easier to do it just generically as f, and then be able to change the function f, and I don't know. I could look for it. Well, no, I don't want to do that. Okay, but so then here's one thing we didn't do. So this is showing the approximate for 0.4 and the exact as red. So if I were to decrease h, every time I decrease h, the interval becomes smaller over here, and the approximate rate function converges on the exact. So there's a smaller h, still smaller. And then when h is 0.005, they pretty much coincide, almost. So if we had more time in the semester, this would be an assignment because I want you, but because of the project, we have limited time to do your projects. We'll make it extra credit if you want to do it for extra credit. Okay? So this is a lot to do, but it would be super valuable. To be able to create this, you know your stuff. You really know your stuff. Questions on this? Yeah.
View one doesn't do anything. Like view row one doesn't do anything for us. Like we don't have to worry about that.
Yeah, if you just want to do, yeah, right. So view one is all for the chunky method. So where it's just 0.4, 0.4, 0.4. So that, but you don't have to do that. So just, I'm more interested. So yeah, show it up. You could show it in this here. So with what I just showed you, it's both. It's both. So that's plenty. That's plenty. Okay. View one shows that this method. View two is the transition. Then view three is the smooth, starting the smooth method. Other questions? Okay, cool. I hope lots of you try it. Are you good?
It's not really a cheesy question.
Go ahead.
Why did you choose to put the rate function on the left this time? Like
Because it was the same. Because it so that when we did the whole, I always had rate on the left and accumulation on the right. So just to keep it consistent, the accumulation's on the right, rates on the left. Other questions? Okay, and
Does that H go away when your H changes the little blue?
yeah, so as soon as I take it off of 0.4,
It goes away too?
yeah, it just, so there's a different H. So it's still, everything's still right mathematically, it just doesn't show that thing anymore. Okay, so you can have the rest of your time to work in your groups on your project, or you can work on falling marbles, and I'm here to help you with that if you have questions. Yes, sir? Okay. Would be beneficial for more class or just on what you're listening? If your whole group is here, then you want to work on your group project, okay? Your group project. What's that? Oh, actually, thanks. Does any group want your proposal that you turned in for the rest of class to look at?